All right, so what's going to happen today? You are going to be doing an example, and of course, we're going to be doing also the splice length. Splice length is very similar to development length, with just a little bit of modification in the equation. But what does it mean by splice? Splice that you're going to have a rebar, and because of the typical rebar length provided or available to you in the market, you cannot really go as long as, let's say, 60 feet or 70 feet. You cannot do it this way. So you need to splice the rebar. Splice the rebar means you're going to have one rebar here, you bring the other rebar next to it, and this is what you call here lap splice. So you don't really need to weld it. You don't do anything to it. So what's going to happen, the force is going to be coming out of the first rebar to the concrete, surrounding concrete, and then get transferred to the other rebar here, also through the surrounding concrete. Now, the first example that we have on this development length, it says here example 5.1 or 5-1, calculate the tensile development length required for number 8 rebars. So the first item we have here is going to be the rebar size, and based on this, we have Epoxy sub S. And it says here top rebars. So they give me definition. They say that you're going to have more than 12 inches of fresh concrete. It's going to be right here. Look at this. So it is not about the total depth of the concrete. It's going to be how much concrete that you have below the rebar itself. It is not measured from the center of the rebar, right? It is measured from the bottom of the rebar itself. Now, this analysis that we are doing here is going to be specific to this rebar within the beam. Meaning, if you have some bottom rebars with the same size, same spacing, it's going to have different formula, different length, and it's going to be different treatment. It says here that you have lightweight concrete, so lambda factor is going to have an effect. And also it says F sub y is going to be 60,000. This is grade 6 steel, and the concrete strength is going to be 4,000 psi. And they give you also the stirrup, which is a pi. They say that this is going to be number 4. This is going to be half an inch from here to there. Same thing is going to be half an inch. And this is going to be important to figure out C sub B, for the edge distance or the cover distance, if you like. All right. It says here K sub D is going to be equal to 71.2. Now, I'd like to see where this is coming from. So I'm going to go back here. It says 4,000, 60,000, number 8. I'm going to go back, look at this table. It's going to be F sub y is going to be 60, 4,000. I have a factor here of, you can just look it up. It's going to be 71.2. Here's a factor for this equation. So you don't really need to do it if you have this table. But the tricky part, when you have 3,500 psi concrete, in this case, you cannot really use this table. You need to use the equation. So I'm going to say I have here 71.2 for the case of D. I said, okay, this is good, 71.2. Now, it says here, when you have top rebars, because in the problem it says that you have more than 12 inches of fresh concrete below the rebar. So I'm going to go back here again to epsilon psi sub T. For the top rebars, it says it's going to be 1.3 versus 1, right? So 1 is going to be for all other reinforcement. This includes horizontal bottom rebars and vertical rebars. So if you have a column in one of these exams, and I say here, determine the development length for the vertical rebar of the column, you cannot really ask yourself, this top rebar or bottom rebar is going to be vertical rebar, it's going to be covered with this psi sub T of 1.0. So, okay, good. Now we're done with the first one here, case of D. We're done with the psi sub T. In this case, in our problem, specific problem here, it's going to be more than 12 inches. Top rebars is going to be 1.3. And for the epoxy coated, I didn't read here anything about coating. So when you don't see anything about coating, consider it to be uncoated. This is going to be conventional rebars. And psi sub E is going to be equal to 1.0. Also, it says here for the size, the rebar size is going to be number 8. I'm going to go back here to the size factor, psi sub S. It says when you have number 7 and larger, you go with psi sub S of 1.0. Okay, the rebar I have is number 8, so psi sub S for the size is going to be 1.0. If you have lightweight concrete, we have this lambda of 0.75. In this specific problem, it says that you're going to have your lightweight concrete. If I have normal weight concrete, I would have used lambda of 1.0. There's one check. Actually, there's 2 checks that you need to do. The first one is when you do the multiplier of, or when you multiply psi sub T times psi sub E. Now you take 1.3 times 1, and it cannot be more than 1.7. So what happened if there's more than 1.7 in your analysis? You just use it as 1.7. So 1.7 is going to be like a cap. It's going to be the top value, the
I have a
maximum value.
question. For lambda, you said if it's not lightweight aggregate, is 1.0?
Yeah.
Okay.
So, yeah. I don't know if you have it here, but this is what we used to do in the past. When you have this lambda factor for the lightweight concrete, we have usually two values that we use. If you have lightweight concrete, use 0.75. If you have normal weight concrete, use 1.0. All right. How about C sub B? I'm going to have here two values for C sub B. If you recall, C sub B is going to be the cover to the rebar. It's going to be the cover of the rebar, right? C sub B. We have two ways of doing this C sub B. When you have more than one rebar next to each other and you're working on this rebar, right? So you need to check the top cover, and this is going to be C sub B1, it's going to be C sub B2, and C sub B2 is going to be going to the midpoint between the two rebars, right? So it's going to be C sub B1 and C sub B2. When this C sub B is going to be larger in value, actually this is going to be good for you because you're going to have here enough concrete surrounding the rebar so that the stress or the force is going to get transferred from the rebar to the surrounding concrete. So when this is tight or this cover is tight, you need to make the development length larger, or the splice length is going to be much larger than what you would get if you have here bigger, like confinement or concrete cover surrounding the rebar. So what's going to happen here? We're going to be comparing CB1 to CB2, and then we're going to be taking the smaller. I have here some analysis for CB1 and CB2. As you see, it says here for CB1, which is the top, I'm going to have here 2-inch clear. That was given the problem, the black type ones, right? This from the problem itself. Now I start to add my analysis to it. I say it's going to be finally 3 inches because this tie or the stirrup is going to be 1/2 inch. So I'm going to have here 2 plus 1/2 inch plus 1/2 of the rebar diameter, like the rebar radius. For number 8 has a diameter of 1 inch. It's going to be 1/2 inch. So you have 2 plus 1/2 plus another 1/2. You're going to have here 3 inches. This is from this point to that point. So okay. How about CB2? It says here that the clear distance is going to be 3 inches from the face of the rebar to the face of the rebar. So, okay, good. Now, the distance from the center of the rebar to a point which is at the mid distance between the two rebars is going to be 1.5 inch, which is this little arrow, right? You're going to have here 1.5 inch, which is half of the 3 inches, plus 1/2 inch. So we're going to have 2 inches for CB2. CB2 is going to be 2 inches. Now, which one to use? I'm going to say I'm going to be taking the smaller. And I guess you guys understand why the smaller, because the smaller is going to be controlling the length. When you go to smaller cover around the rebar, you're going to go with longer development length. Okay, so I'm going to be taking here the smaller. I'm going to go back one slide to look at the other information I have. KTR, as we said, we're going to be assuming to be equal to 0. Now, C sub B plus KTR divided by DB. Now, this one here, we're going to set it to 0, right? I'm going to cross it out. C sub B is going to be equal to 2 inches, and the diameter of the bar D sub B is going to be 1 inch. Now, this is going to be the other check. If you remember, C sub B plus KTR divided by DB is going to be maximum of 2.5. It's going to be the other check, very similar to this check, but the limit is going to be here 1.7. Here's the limit is going to be 2.5. Let me go back here a few slides to show you what I'm talking about. This is going to be the check that you do. KB plus KTR, as we said, is going to be equal to 0. So C sub B is going to be 2 divided by 1 is going to be 2. And this is have a maximum or a cap of 2.5. So okay. Now I guess I have all the values I'm looking for, right? So what's next? Just use the equation. Here's the equation, L sub D. L sub D. You have here the lambda factor, right? Lambda factor is going to be increasing L sub D. So when it's going to be equal to 0.75, when you take any number here divided by a fraction, you're going to be getting longer number. K sub D, I'm just going to be using here all the values that I was able to find out in the previous 2 slides. And at the end, I'm getting 61.7 inches, 61.7. The last check is to compare it to 12-inch minimum. And they said, well, I'm going to be going here with 62 inches for the development length. This is a lot. You're talking here about 5 feet and 2 inches. In many cases, it's just simpler if you provide a hook, because this is here straight development length. If you're just going to be going here with straight length, so L sub D is going to be straight development length. Let's look here for the second example. It says calculate development length required for number 9 rebar. It's good once you have here the size. 15-inch thick reinforced concrete slab. Here's the thickness, 15-inch. I guess the thickness is going to be important to figure out if you have enough concrete below it or not. If you have more than 12 inches, it's going to be top. It's going to be 12 inches or less, or it's going to be less than 12 inches. You're going to sort to be bottom rebars. It says this is a slab, no ties. Of course, no ties. I understand. Yes, I don't really need to say that, right? So you understand. In concrete slabs, we don't put any ties, unless you have a special case that you need to use ties in. F sub Y is going to be 6 KSI, grade 60 rebars. Concrete is going to be 4 KSI, normal weight concrete. In this case, lambda equals, so lambda equals 1.0. So, okay, and the bars are epoxy coated. So now I have an epoxy, right? So let's look here at the spacing, because it says number 9 at 8 inches. So the spacing from center of the rebar to center of the rebar is going to be how much? It's going to be 8 inches. Also, I have this cover, right? So what is this? This is the other section, right? Look at this. It's going to be the other section. If you cut the section here, this number 9 at 8 is going to be what? This rebar here that we are pointing at is going to be this rebar, the round ones, the circles, right? Because we cut the section right here. And actually, the reason that we are doing this, because we'd like to figure out how much is the cover in this case, right? I said, okay. The cover, as it says here, is going to be 3/4 inch clear. It's going to be very small. Now let's go here through all the factors. First factor from table 1, based on 4060 KSI, you have the 71.2, very famous value that people would use, right? Now you're going to have top rebars. Why is that? Now I want you here to look at this. This is going to be number 9, which means 1 1/8 of an inch. You have, let's say, 3/4. When you look at the amount of concrete below this, you're going to see it is going to be more than 12 inches. You have 3/4, let's say plus 1, just make it 2 inches. Total slab thickness is going to be 15, minus 2 is going to be 13 inches of concrete. More than 12 inches. So I'm going to say it's going to be top rebars. The size of T for the top factor is going to be 1.3. Epoxy coated with certain spacing. So I can back check this. It says here, when you have 3/4 inch with 3 dB, right? 3 dB is going to be equal to how much? 3 times the bar diameter. It's going to be like 3.4 inches. Now this is going to be smaller than 3 dB. It means your psi for the epoxy is going to be 1.5. Yeah, see, this is not really clear. So I'm going to go back to that slide and check for this epoxy coated factor. So, okay, here's the epoxy coated factor. When you have epoxy coated factor, you're going to have here 3 values. 1.0 if there is no coating, like conventional rebars, regular rebars. And then for the epoxy, if it's going to be closely spaced or the cover is going to be small, in this case, you're going to be going with 1.5. Otherwise, it's going to be also epoxy coated, but you have bigger spacing and bigger cover, you're going to be going here with 1.2. So when do you think you're going to be using 1.5 for the epoxy coated factor? Is when the cover is going to be less than 3 times the bar diameter. Let's say that you're talking about number 8. Number 8, it means that you have 3 inches. Now, in this case, I don't really have 3 inches of concrete cover. All what I have is only 3/4 inch. So it is true that I'm going to be here. I'm going to be with 1.5. This makes sense. Yeah. So, okay. For the size, number 7 and larger, for the size factor is going to be 1. Normal weight concrete, lambda is going to be equal to 1. So I'm going to put here an arrow next to it. I'm going to say normal weight concrete. All right, now let me try here the product of psi sub T times psi sub E. take the top, and then also use psi sub e for the epoxy. What number do I get? 1.95. What's my max? 1.7. So I'm going to be using 1.7 instead of 1.95. So when it comes to the equation, psi sub t times psi sub e is going to be only equal to 1.7 as the limit, the maximum value. How about CB1? CB1, I'm going to say, let me figure out from the center of the rebar to the top concrete. CB1 is going to be the top one, based on the concrete covering the top. So I'm going to say, how about here? How can I do it here? I'm going to say, from this point, from the center of the rebar, all the way to the cover. How much is this? It's going to be the question, right? This distance here. It's going to be very small. So I'm going to say it's going to be equal to 3/4 of an inch, the cover, right? Plus 1/2 of the rebar diameter. So, okay, let me see the analysis for this. So for CB1, 3/4 of an inch, you can say this is here is going to be the cover, right? And this is going to be the bar diameter divided by 2 is going to be the radius. So it's going to be 1.314. The other CB is going to be the bar spacing, right? It's going to be from the bar to the bar. It's going to be half the way between a bar to a bar. So we're going to say, what distance are you talking about? We're going to be talking about the distance from this rebar to half the way between the two rebars. When it says here, number 9 at 8-inch OC, what is this OC? Can someone help me with this?
On center.
On center, which means center to center, right? So if you like, you can just take this 8-inch and divide by 2, because this is going to be equal to that distance, right? So you don't here give you the clear distance like in the previous problem. Now, in this case, you give you the center to center spacing. So I'm going to be taking it to be 4 inches. Now compare 4 inches with the top cover center of the rebar spacing. Now, which one controls? I'm comparing here 1.3 inches to 4 inches. I'm going to say, I'm going to be using this value. So one of the checks, again, for the limit, when you multiply psi sub t times psi sub e, and you cannot go above 1.7. The other check, when you do here CB plus KTR, that usually we consider to be 0, right? Divided by D sub B. And in this case, I have it as, once you put the values, it's going to be 1.165, less than 2.5. It's okay, I can use this value and not use this value. Now let's look here at the final equation. The final equation, this lambda is 1, normal weight concrete. Psi sub t times psi sub e is going to be only 1.7. Look what happened here. I'm not going to be using the actual values for these two values, these two factors, because I have a limit of 1.7. So, okay. For the bar size, I have the factor is going to be 1. CB plus KTR, as you know, it's going to be equal to 0, and the value is not above 2.5. I can safely use 1.165 taken from here. What is this 71.2? It's going to be from table 1, right? This is going to be K sub D, and multiplied by the bar diameter 1.128. Here's the number I'm getting. Look at the number here, 117. This is a lot. You're talking about here 2 feet, almost 2 feet. You're shy of 2 inches, right? And your limit here, or the minimum, is going to be 12 inches. So I'm going to be going with 118. And if your choice would be 120 inches, I'm going to be okay with it. This makes sense, of course. I'd use 120 inches.
Professor.
Yes.
Would you remind me what are the LD values used for? Is it just for the curvature of the hook?
No, this is not for the hook. This could be for the straight development length, not the hook. What is the straight development? This could be the straight development. So you'd like to terminate the bar, right? But you don't want to hook it, right? So you just leave it straight. In many cases, this is a very simple way of doing it, like in concrete columns, right? It's just much easier when you do this, and also in beams. Because to bend it, you need to fabricate it this way, and then you need to ship it. And in many cases, you can just have a little bit of additional rebar size or length that you just throw it in the concrete is going to be cheaper for you.
So then it would be the distance from the column to...
It's going to be from the point that you don't need the rebar at to where you end it.
Okay.
Where you stop it.
Got it. Thank you.
So it is not usually it's going to be here, right? It depends on the type of analysis that you do. right?
Mhm.
This makes sense? So let's make it this way. Development length is going to be the distance from the point that you don't need the rebar at to where you stop it, where you trim it. All right, you're good? Alexis, you're good?
Yes, I'm just writing this
Okay,
down.
very good. All right, excellent.
I have a question, Professor.
Yes, absolutely.
For
Go ahead.
epoxy coated, how did we get 1.95?
Okay, the epoxy coated is not 1.95. Let me go through the epoxy coating again.
Because we said that it
Yes.
was greater than
Yes,
1.7.
absolutely. Yes,
Oh.
I'm coming to it. I'm coming.
Mhm.
I just want to review. I know that you didn't ask about this specifically, but since this gave you a question, so let me cover the whole thing about the epoxy coating. For the epoxy coating, you have two values. So if you have epoxy coated rebars, you have either 1.5 or 1.2. Depends on the cover and the spacing between the rebars. So if the cover is going to be small, what does mean by small in this case? When the cover is less than 3 times the bar diameter. Now our cover in this case with 3/4 inch and the bar diameter is above 1 inch. So I know it's going to be, I mean, you cannot really say that the cover is going to be more than 3 dB, so you're stuck here with 1.5. So the epoxy factor here is 1.5. And because the rebar is a top rebar, the psi sub t is equal to 1.3, right?
Yeah.
Now I have one check here. It says if psi sub t multiplied by psi sub e, you have a maximum of 1.7. Now multiply 1.3 times 1.5, you get 1.95. You say my limit is going to be only 1.7. Let me show you how this happens. It's right here. Look at this. In the first example, when you do the multiplication, you end up with 1.3, so you just used it. Look at this here. You just use here 1.3. For psi sub t and psi sub e, you just decide here to use 1.3. But when it comes to the second example, I did this multiplication here. I ended up with 1.95. So my limit is 1.7. So I'm going to be using here 1.7. So I'm going to be coming here and just use 1.7. Good question, Chicken. Good question. Thank you. All right. More questions?
I have another question.
Yes, please.
When we determine our development length, why don't we compare it to 12 inches?
Because in the code, part of the requirements, right? If I'm going to take you back here, LD minimum 12 inches.
Oh, okay.
So
right.
I know that when you look at this number here, you say, who's going to compare it with 12 inches, right? You have 5 feet. I mean, there's no comparison. But for academia, you need to do it, right? And also, if you're doing a spreadsheet for this, which I recommended for you guys, if you are planning to work in this business, structural engineering or concrete design, maybe you'd like to have a quick spreadsheet to do this for you, right? So if you're doing a spreadsheet like this, you need to put your minimum to be 12 inches. Even with this, you're gonna say, wow, I have like 10 feet. Who cares about the foot? I mean, why would you do the comparison? I'm gonna say because code is asking you to do this check, this comparison. You're good?
Yes.
Right, great. Gonna go here to slide set number 16. That was number 15. Also development length is gonna be the second set, right? It's about development and splice length of reinforcing bars. Now, instead, now you have seen yourself for number 9 rebars, I needed 10-foot development length, which is too much. And also for this example 5.1, I ended with roughly 5 feet. So I think that this is a lot. In many cases, I don't have a space to put this 5 feet or 10 feet. So this is the reason that we're going to be looking here at a different solution. Instead of having the straight development length, we're going to provide here a hook. We call this 9-degree hook. So this is a rebar coming from here, and you see the extension. And this is going to be the critical section. So what's the critical section? It's going to be that section that you don't need the rebar behind it. So the tension is going to be in this side. All the work is going to be in this side. And this is where you'd like to end it. Now this length from the critical section to the end of the hook, I'm going to call it LDH. So development length for the hook. Same thing here. LDH, development length for the hook. About this one here, same thing, LDH. So, okay. I can have 9-degree hook, or I can have 180-degree hook. So great. How about the hook dimensions? Hook dimensions, usually, if you're gonna have this 9-degree, is gonna be 12 times dB as an extension, measured from that point. If you have 180, so after you bring it around this rebar, you're gonna bring it here, right? 4 times dB, and it needs to be more than 2.5 inches. In reality, you don't really need to have a rebar here. You can just have the rebar here, this one, the main rebar, that you're gonna be hooked like this. So the reason that they give you this dash to tell you that in order for you to bend this rebar, you need to bend it on a given, let's say, radius of this much. So this is gonna be for the bender, this is gonna be for the machine itself. And this is gonna be based on the bar size. Look at this. This is gonna be equal to 6 dB for number 3 to number 8. All right, so I'm gonna say, if I have number 8, like 1 inch, what diameter would you use here? What's the radius for the bending? Yes, say radius for the bending. Let me do the analysis. It's gonna be simple, right? It says it's gonna be 6 times dB. If this is number 8, so let me put it here. I'm gonna say here for number 8, what's gonna happen? Gonna have dB of 1 inch.
Times 6.
Yes. Remove it. Times 6. So I'm gonna say D equals 6 inches. Therefore, the radius for it, so I'm gonna call it this R is gonna be also uppercase, since it's gonna be uppercase also. I'm gonna say what? It's gonna be 3 inches, right? So this radius is gonna be 3 inches. So just hypothetical question here. What happens if you bend it in a smaller radius than 3 inches for the same bar size? What's gonna happen? Would you have any trouble?
Could you repeat the question?
What happened if the radius for this bending, let's say that you are on a job site, and all of a sudden they said, is it really critical to bend it on 3-inch radius for this rebar? Number 8. Can we do it in 2 inches? What's gonna be the consequence in this case?
It won't be that
Depend-
many degrees.
So what would you have any damage in the rebar? Yes, say absolutely. Yeah. The rebar is gonna be full of cracks from here, from this side, from the tension side. It's gonna fail. And you can watch some videos on this. So actually, this is gonna be kind of minimum 3 inches. So if you like to go to 4 inches, it's gonna be nicer, right? So you don't really wanna have this type bend, you know? Otherwise,
so these
it's gonna
formulas
break.
are used for just to make sure that the rebar doesn't
Yes,
break.
doesn't break,
Okay.
right?
Thank you.
I have a rebar sample, and this sample, it was bent to a tighter distance, is big size. It was number 10 rebar, and you can see the cracks. I have the actual specimen here in the office. So maybe one time I'm gonna show it to you guys. I said, okay, this is gonna be the really 2 important hooks that we're gonna be using for rebars. This one here is used for cross ties, and for the stirrups, they call this 135 when you have the rebar coming this way, and from this side you can do here 9 degree, like in this side here. Okay. So what is LDH? Let's say here's a critical section.
Professor, one
Yes.
quick question. Could you go back to the 135 rebar?
I can, yeah.
So we're still going to use the same formula for even the 135, right? Or am
Yeah.
I reading this wrong?
Yeah.
Because I see D is greater than or
4
equal to
dB.
4D.
Right.
Oh,
Yeah,
only
look
for
at
5.
this. This one here
Mhm.
is how much for this
Uh,
dB? Yeah, it depends on the bar size, right? And this gave for all steels, D and D and D, right? Okay.
Oh, okay. Roger, thank you.
So this gave for number 3 to number 5 only. Yeah. So this can be the critical section, and this can be LDH. You can do here 180, or you can do what? You can do 90. Now, do you have ties? If you have ties, this is gonna be different discussion, right? Because ties can provide confinement. You guys remember the term confinement, which means concrete is gonna be stronger. So transfer or the force from the rebar to the concrete is gonna be easier. So just imagine that you have here tension force, right? When you have confinement, the concrete strength and the bond between the steel to the concrete is going to be higher, and in this case, you may end up with a smaller hook length. And we call this enclosure, right? This is going to be the enclosed 180-degree hook. Now let's see here, what equation do we have? I'm going to say the equation is going to be much simpler. So the straight development length was tougher, right? It was longer equation. It's going to be very simple. It says 0.02, this is going to be LDH for the hook, 0.02 times psi sub E. I guess we heard about this psi sub E, right? For the epoxy, but it says here it's going to be only 1.2 for epoxy coated. So I don't have here two values, 1.2, 1.5, and 1. In this case, it's going to be only 1.2, regardless of the spacing. F sub Y, concrete strength, F prime C, steel strength, F prime C, concrete strength, lambda factor, lightweight factor, and dB is giving you the bar diameter. Now the minimum LDH, now for the straight development, we have a minimum of 12 inches. Now the minimum LDH is going to be 8 dB or 6 inches. So I said, okay, let me try here one example. One example, it says determine the anchorage development length required for tension, top rebars, and here's the conditions. 3,000 psi, normal with concrete, 60,000 psi for the steel, and it says uncoated number 8 rebars are top rebars. Okay, top rebars uncoated, this is good. Then the epoxy is going to be equal to 1.0, and a side cover with the main rebars, 2.5 inches, and expect the use of 180-degree hook and compare. Meaning, now I'd like here to check and see the length that I need. If I'd like to go here with straight development length versus a hook. So the first one, L sub D, we have done it before. I have seen before, I have no problem with it. We have used it, and we should be able to use it easily. For LDH, is going to be now the new analysis, right? This is going to be the thing new here in this slide set. We have here some factors, and once I need it, I'm going to back to it. I'm going to come back to it. So, okay. Now, this slide here is going to be for the straight development length. So I have here psi sub T, psi sub E, check the factor 1.7. If you have top rebars, going to be 1.3. Psi sub S for the rebar size, normal with concrete, uncoated. And then you have CB to the side and to the top, right? It's going to be based on this, the spacing, and based on the top cover, you know, all of that. So we went through this already. And then you do another check for CB plus KTR, which is usually equal to 0, right? And then you have a maximum of 2.5. Now run the analysis.
What
Yes.
does KTR stand for again?
KTR, this is for the ties. If you remember for the ties that we ignored, we said usually just conservatively use it as
0. Oh, okay.
as 0. I'm gonna say yes, it's right here.
Okay,
Here's
just double check.
KTR. Yeah,
Thank you.
here it is. Right? We just say just use it equal to 0. Now for this example, for the straight development length, okay, now we know this equation. Okay, it says here 53. Finally, I'm gonna be using maybe 54 inches. Now this gives me the end of the column here, right? This is the end of the column. You see where the column ends? This is our column in the picture, right? Let's give you the column. The column length was actually 24 inch. Now it says this development length is going to be equal to 53.4 inches. So like 54 inches. So what does it mean? It means I'm going to be using a bar that sticks out like this. So it does make sense, which means the code is asking you to build an extension of the beam like this. It's going to be coming outside of the building, right? To encase this 54 inches. So if you really want to use a straight development length, you're going to be in trouble because you're going to have a piece that sticks out of your building. And the length of this is going to be maybe 3 feet, right? So that you have a total of maybe 5 feet. It's going to be 2 feet here for the column length, plus 3 feet for this extension of the beam. It's going to look ugly. It's going to cost you for the formwork. This is the reason now, instead of having this straight development, I'd like to use 180-degree hook. I'd like to hook it right here, which means come here with some hook like this, right? And then connect the rebar like this, something like this, right? So this is what I'd like to do. So in this example here, we're showing you like by step why the use of this straight development length is gonna be like painful and doesn't make any sense. And the use of the hook is gonna be much cheaper. So it is true that here, if you're gonna be going to an example like this, right? And you have extended beam, it's gonna be just easier if you throw the bar there. But in this case, because this is gonna be a column, it's gonna be the end of the beam, you're gonna be in trouble, and then you need to do an extension of the beam like this. It's gonna be sticking out of your building, and doesn't make any sense. So we're gonna be doing here 9 degrees or 180 degrees hook. Here's the equation. The equation is simple, as you see it here. 0.02. If psi sub b only has one value, right? It's gonna be 1.0 because it's gonna be uncoated. F sub y 60. Lambda, normal weight concrete is gonna be 1. Concrete strength 3000. D sub b is gonna be 1 inch. You have only 21 inches. So this is beautiful because you can fit it within this here. You can just do here a hook. So once you put here a hook, everything is solid. You don't need this now, right? If you have a hook development length.
So
And then,
if
yes,
we increase the epoxy coating or the coating on the rebar, that would just increase our LDH, right?
exactly.
So,
Yes, absolutely.
okay, thank you.
Yes. So with that, I said, well, this looks like it's gonna be a very good option, 21 inches versus 54 inches. So I said, you have more factors here that I just skipped. Now I need to go back to it and see what are these factors for. It says you have a factor here, reduction factor of 70%. So you can use 70% of the length. So the reduction factor, let's say, is gonna be 30% reduction, which means 0.7. It's gonna be for number 11 bars or smaller. Okay, now in this case, that was number 8. So this is good. With side cover smaller than 2.5 inches, and for 9-degree hooks with cover on the bar extension beyond the hook, not less than 2 inches. So, okay. So if you have a cover of 2 inches and you have 9-degree center hook, I should be able to use this 0.7. I have another reduction factor of 0.8 and then give you some discussion here. How would you use it? So it is true that you have this LDH and then you have your analysis, but you have additional in the code, in this code section here, you have additional reduction factors. Same thing here, 0.8 when you have 180 degree hook with number 11, and you have a smaller bars that are enclosed wooden ties. You can see wooden ties. You see the ties and the spacing? Look at this. And the space, you're gonna go back here. You say, you remember this enclosure, right? So if the spacing between the ties is gonna be smaller than 3 dB, which dB of the splice bar or the developed bars, in this case, you can use a factor of 80%. Also, we have the same factor here when you have AS required versus AS provided, right? So you can have a reduction here in the length of the development. So let's say that you need 5 square inches and you provided 6 square inches, which is very common. You really need to provide a little bit rebars more than what you really need, right? So the provided is going to be most likely more than the needed or the required. So in this case, you can reduce it by dividing the required by the provided, multiply by L to PH to reduce it. So let's see here, what factor did we use? The factor we used, it was 0.7, and the factor of 0.7 for rebars with side cover more than 2.5 inches, which means this condition here, right? So I said, let me take here 21.9 multiplied by 7. That was equal to 15 inches, which is great. Maybe you can go to 16 inches or 18 inches as long as you can fit it within the column without having this beam extension. So, okay, now splices. What about the splices? What's going on? The splice, when you have this lap splice, there is no weld. So let me put this here. No welding. Right? They're not welded to each other. You just put next to each other. So great. So what happened? You have the tension. It's going to come from here, and you'd like to have continuation in the tension force. So what's going to happen? This tension force is going to get transferred to the surrounding concrete, and then now once the concrete is going to have all of this stresses, it's going to get back collected to the other rebar, to the splice rebar. So you put the tension force here, now you are able to bring it to the other side. This is what we call here lap splice length. So let me write it down. It's going to be lap splice length. Lap. And the equation for this lap splice length is going to be simple. What you need to do the development length, the way that we learn how to do it, the straight, of course, not the hook, and just multiply by 1.3. So nice. It's going to be the same equation. So you don't have here a new equation. You just need to multiply by 1.3. And according to the code, what is the minimum lap splice length? 12 inches. Okay, great.
Professor, is the LD, is that with the reduction factor included, or is this
Yes.
a different problem? Oh, okay.
Yes, but this now for a splice. So after you do your analysis and find out L sub D, just include the factor of 1.3.
Got it.
Okay. Is this the only way that you can splice two rebars? You can say no. There's also couplers. Did you guys hear about couplers, mechanical connectors? We have some couplers like mechanical connectors, or you can weld it if you want to. But if you weld it, this length is going to be much shorter. It can be maybe 6 inches only. So instead of having 10 feet, if you provide welding here between the two rebars, you can make it maybe 6 inches to 8 inches. Or you can provide a coupler. A coupler is going to be like a box. It's going to be something like this, right? So one rebar is going to be coming like this through it, right? It's going to be coming like this. And the other rebar is going to be coming from the other side. And then this is going to be just a coupler. So what's going to happen? The force is going to be coming from the first bar to the coupler, and then again from the coupler to the second bar. So the good thing about it is going to be very short, right? The length of it is going to be much shorter than the splice. The bad thing about it is that you need to have enough spacing between the rebars, which in some cases you don't have. In some cases, you don't really have enough spacing because the diameter of this coupler, I mean, it's not going to be like, if this is number 8, this diameter is going to be maybe 2.5 inches. So you really need to have enough space. And besides, there's also a cost with it, right? A cost in terms of the material and for the labor to install it. While in the lap splice, it's going to be much cheaper. You just put the two rebars next to each other. So there's nothing special about it. This is why this is going to be the first one that usually you'd like to use, and you'd like to think about using lap splice instead of having coupler or welding splice. Any question? So, okay. Now let's do the in this example here. Just want to explain what's going on. So in this problem, I'm going to start with this slide, not the previous one. I'm going to say I have the beam span, right? Simply supported. The span is 24 feet. Here's the concrete section. And you give me here weird dimensions like 16 and a half. I'm going to say fine. I mean, why not 16 inch? But this is the way it is in this example taken from the book. And they say the depth, D, not the total depth, like the total depth of the section. It says here 18 inches. They give you the clear cover, right? 1.5 inch. And they say that you have number 4. So you have number 4. It's going to be ½ inch tie or stirrup. At the bottom here, you have 6 number 7. So you can be, you should be able to find out the spacing from a rebar to a rebar. And now also they say, here's the moment diagram. You know, here's the moment diagram. It's going to be W squared divided by 8, right? I guess you guys now are familiar with this value from structural analysis. And they say now, if you have here 6 rebars, and this is going to be the rebars required, let's say here that you really need exactly 6 rebars, 6 number 7. So you know that each one of this rebar, it has a certain resistance when it comes to the moment, right? Meaning, for each one rebar you put here, you have phi mn for it. Are you guys following me? So we're going to say phi mn, right? It's going to be equal to, how much is this? How much is that? And it equal to 6. Let me just call it equal to 6. 6 what? It could be 600 kfoot. Just some number here. I'm gonna call it 6. Which means this is gonna be 6, right? For what? For all 6 rebars. How about phi mn for one rebar only is gonna be equal to how much? So I'm gonna say phi mn for one rebar is gonna be equal to 1 for 1 bar. Do you guys agree? If 6 rebars is gonna be covering 6 units, right? So one rebar is gonna be covering only 1 unit of this moment diagram. So now in this case, this is gonna be m sub u, because when you say here moment diagram, it means m sub u, right? It's gonna be here m sub u, not phi mn. But in this case, we say m sub u equals phi mn, right? They're equal to each other. This is the way that we do our design. We set the demand equals to the capacity. So I'm gonna say this is gonna be actually this is gonna be the demand curve, right? This is gonna be like this, W squared divided by 8. Is gonna be equal to the capacity of the 6 rebars, and each one of these rebars is gonna be covering 1/6 of the entire moment diagram. So here's the first rebar from 0 to 1, right? It's gonna be covered by the first rebar, second rebar, third, fourth, fifth, and sixth. I said, okay, so this means I have a good design because phi mn is gonna be equal to m sub u. This is gonna be the demand, this is gonna be the capacity. This one we call the ultimate or the design moment, right? So I have here a few names for it. I say this is here, m sub u is, I call it here demand, design moment, right? Do you have other name for it? Ultimate, right? Ultimate moment. So what's the ultimate moment? It's gonna be the same as demand, same as the design moment. Phi mn is gonna be the capacity or the strength. So in this case, I'm gonna say here, phi mn is, I can put it this way, I'm gonna say capacity and also strength, right? So I have two names for it. I know I went through this before, but it's usually good to remind myself and remind you guys. Now, once I set them equal to each other numerically, I can take this moment diagram, divide into 6 slices or 6 sections, and each one of them, right, each one of these values is going to be supported by one rebar. So what's the importance of that? I'm going to say the importance is, do you really want to put all the rebars from the end to, from one end to another end, from the beginning to the end? Do you need all of the 6 rebars? Yes, you know. I need the 6 rebars only at one section. You see here? So what's gonna happen? What's gonna happen after? I'm gonna say once you go here, right to left, you don't really need 6 rebars. Maybe you need 4 rebars. So I'm gonna say, okay, can you give me where exactly you can drop the 6 rebars and make them 4? I'm gonna say drop the 6 rebars and make them 4 is gonna be right here. How about the point at which you can drop 2 more rebars of the 4 and just make them 2 to the end? I'm gonna say it's gonna be right here. This give you the point, right? The x distance. Meaning the rebar demand to capacity is going to be running this way. So in here, right at this point, all what I need in this section, how many rebars do I need? We're going to say, well, here's the moment demand. You can set equal to the capacity. So it's going to be how many rebars? It's going to be 4. And at this point, how many rebars do you need after this? I'm going to say I need 2. Meaning, I may, just theoretically, I may put from here to there, how many rebars do you put here? I say 2 rebars. And from here to here, I'm gonna put only 2 rebars. And from here to here, I'm gonna put additional 2 rebars. So in here, I'm gonna say I have here 2 number 7, right? And this give me 2 number 7. Let's give you another 2 number 7, which is just 2 number 7. Now you come here and then you say, let me cut a section right here. How many rebars you have to resist the moment? You say 2 and 2 and 2. I have total of 6. Say, how about if you cut the section right here? How many rebars do you have in this section? And say, well, I cut here 3, 2, and 2. I have 4. So the capacity is going to be right here. How about the demand? I'm going to see demand is going to be right here. So the demand is going to be this black line, right? Yeah, say, how about if you cut the section right here? Now let me move the section. I'm going to be cutting it here. How many rebars do you have? I'm going to say, I have, look at this. This is what I have, the red one, right? I have capacitive 2. How about the demand? I'm going to say demand is going to be the black line is going to be here. Therefore, I'm good. So actually, I don't need to run all the rebars from the one end to another end, from the beginning to the end of the beam. I can curtail it this way. I can trim the bars at certain locations based on the demand to capacity that I'd like to keep. So this red line is going to be the capacity line, right? If I'm going to be doing this curtailment. And this black line is going to be the demand. So this is going to be one way of thinking. Another person may think and say, let's just put all the rebars. So we're going to say, okay, so what does it mean? Where's the capacity now line? You say the capacity line is going to be from here. Look at this. It's going to be from this point. You just do it a little bit higher, and then after that, I'm going to change it all the way to here. This give you your capacity line here, right?
But that would mean that the price would increase, right? Because of the rebar and
Yeah.
the labor.
So I just kept the rebars straight. This is what I've done. So here's the capacity. Capacity is going to be 6 bars, right? 6 units. This is going to be the capacity. But I'm not going to change it throughout the entire beam. This is going to be one option. Just keep it like this. And the other option is to put 2 number 7 with this length, 2 number 7 like this, and then additional 2 number 7 like this, just to save as much as you can. Now, someone's going to say, why didn't you say 3 rebars? I'm going to say now, you need to keep symmetry, right? You need to keep the symmetry when you're curtailing the rebars. So you're going to say, where's the first 2 rebars? This 2 rebars, right? Where are these? And say, this rebar is giving this 2, right? So at a certain point, I can stop 2. How about this, the bottom 2? You say, this 2 rebars is giving this guy and the other one, which is on the other side, right? It's going to be this. I'm going to put here an oval shape, kind of, and this one. Then the one, I'm going to put this symbol in there. Oh, I need to draw it. So let me just do a box. So this 2 rebars is going to be the one that lasts to the end, right? This 2 rebars is going to be these 2 rebars, right? This is the bottom ones. Right? This is going to be the 2 that you're going to keep at the bottom here from one end to another end. So you're going to be keeping these 2 rebars at the corners all the way throughout the entire beam. This 2 rebars, you're going to stop them at this location, right? And this 2 rebars in the middle, you're going to stop them at this location if you want. It's going to be one way of thinking.
So, Professor, that's kind of like the last slide set where you just showed where the rebar just got cut, correct?
Where?
I believe it was in slide set 15.
Slide set 15, you know the previous one. Oh,
Yes.
you're talking about this one. Exactly.
Yes.
Yeah.
Oh, okay.
This is the idea that you need to stop it at a certain point. Absolutely.
Right. So
Yeah.
so it would be,
All right.
for example, like right here. So the rebars where it says bar X.
Exactly. You see this bar X and bar Y, and you see this, I put some something around them. So this 2 rebars give you bars Y, and bar X is going to be the continuous rebars.
Got it. Thank you.
So yeah, thank you for asking this question. Actually, this is going to be, someone can say, maybe this is too much. Why don't you just drop maybe 2 rebars? Just this 2. Just drop them and keep 4 straight. I'm going to say it's going to be up to you. We call this a design. It doesn't mean that this is going to be the best design or the optimum design, but it is a design, acceptable design, yes. I mean, in the business of structural engineering, this is going to be acceptable, but there is usually a design and a good design, and the best design, you know, usually it comes in levels. You know. So the question is, does it mean from this point I can just drop the rebar, or I need to provide development length? Again, say, well, you need also to develop the rebar. From the point that you don't really need it, you need to provide this development length, or maybe you need to provide a hook. I said, okay, now let me look what happened. So I'm gonna say, what is the relationship between this X and between this Y? I know that the equation says M is gonna be equal to W squared divided by 8. I have second degree parabola. which means if you take here this x1 or x and in distance divided by L over 2, which is half of the span, right? You take this divided by this squared is going to be equal to y1 divided by y, which is a big value. So here's y, big value, right? Total moment or total number of rebars in this case is going to be 6. And this y1 in this case is going to be equal to 2, 1 and 2, right? And y2 you can take it as 4, right? And then you can figure out this x1 and x2. This gives me a simple geometry problem here. So if you do here x1 in this case, right, is going to be equal to roughly about 7 feet. And if you do here x2, right, it's going to be how much? About 10 feet. Let's say roughly 10 feet. So this is going to be about 7 feet. This is going to be about 10 feet. Now, you'd like also to extend the rebar a little bit. You cannot just make it tight. You cannot make it 6.93. So it says here additional rebar extension is going to be equal to the depth of the beam. Like in this case, it's going to be 18 inch, right? Or it's going to be 12 inches, 12 times the bar diameter, like what it says here. This is going to be the additional bar extension. 10.5 versus 18. So just take it maybe the depth, which is very common. So in this case, instead of just going to 6.93, you're going to be adding here 1.5 feet. It's going to be maybe 8.5 feet. So actually, you're not going to stop the rebar here. Instead, you're going to stop it a little bit here, if you like. And this distance is going to be 1.5 feet. So instead of 8.43, I'm going to make it here 9.5. Same thing for this x2. You're getting here 9.8. You add 1.5 feet. It's going to be 11.3. Maybe you make it how much? 11.5 feet. So the distance here from this point to that point is going to be 11.5 feet. So I was going to say, well, 11.5, and this length is going to be 12. Just make it 12. I'm going to say, absolutely. It's not worth it that I'm going to be trimming it. No, I'm just going to keep this rebar in sort of this point here. I'm just going to keep it straight. This is going to be one way of thinking, right? Now, also, you can do the same thing, right? You can do the analysis that you do here for KB and development length and the whole thing, right? Now, you want to be sure that this L sub D, right, it is going to be less than the length that I ended up with. Meaning, this development length is also measured from this section. So I said, based on the step here, based on the moment diagram and the steps, I ended up with 8.43. Now, let me figure out how much is this L sub D. Because if L sub D is going to be more than 843, I need to go with the larger of the two. So here I said the distance from this point to that point, based on this stepping, right? Because of the demand capacity curve or diagram that I just made here. You can say, let me compare this length with L sub D needed. If L sub D needed is going to be more than 8.43 feet, I need to follow that. I need to follow this L sub D. Meaning I'm going to be doing one analysis based on stepping of the demand capacity, and the other one's going to be based on L sub D, and of course we will be taking the larger of the two. Now let's do here the development length, and let's see what value would I end up with. Now I guess you guys are very good now with this analysis. So I'm going to be doing my analysis, end up with 2.21 feet. So I'm going to say, you know what? I'm going to be using here 8.5 feet, right? Because I was looking for this L sub D. I want to be sure that if I use here L sub D, that I have enough length to develop the rebar. So actually the rebar will need only 2.5 feet to be developed, right? But because the moment diagram and because the capacity diagram, someone's going to say, where's this capacity diagram? I'm going to say this is step in red that you see here. You can call this capacity diagram, and this black curve is going to be the demand diagram. So when I compare this to this, I said, well, I need to stop the rebars at least. It's going to be at 8.5 feet from this point, right? But I want to be sure that this is going to be covering the development length. And the good thing, development length is only needed like 2.2, like let's say 2.5 feet. And for the stepping, I need, for this demand capacity, I need 8.5 feet. So I'm going to go with 8.5 feet. Any questions? Because as you see here, we are done with this slide set. So I'm done with this subject for the splicing and the development length. And we're good for today. So the rest of the lecture, I don't have that much time, but you still have, let's say, 7 to 10 minutes of questions if you want to.
Professor, for KTR, why didn't you put 0 for this one?
This one here, well, it depends on the way that you like to do it. If you like to be conservative, just take it as 0. So I'm okay if in your analysis you decide to put this here to be 0. It's gonna be okay. I don't see a problem with that. But it says, if you remember, a good question, Adolfo. If you remember, we say what? You remember this case of the KTR, right? Conservatively. So I'm okay with it. I'm okay if you are going to be taken equal to 0. But don't forget that this example here, I'm taking it from the book, from the textbook. And the textbook, they solve for KTR, so I need to be consistent just in case if we're going to be going back to the same reference, you don't see here 2 different solutions. But using my analysis, and even when we practice in actual design, we just take it equal to 0, like what you see here. This is what I use.
Okay, thanks.
No problem.
Professor,
Yes.
with the tension lap splices, could you go back to that slide? It's on number 11 of number 16. So you mentioned that there's the coupler, or
Yes.
correct? I guess my question is, how do we do an analysis on this? Would it just be the same thing then?
No. Each product, this is like products, right? Each product is going to be rated for certain value. So let me show you this.
Okay.
Here's one of the couplers, right? Look at this. I hope this is here clear enough. You see this? Here's a coupler. It's just rated. So let's say if you put for number 8, it means this is going to be strong enough to support number 8. So you don't really need to do anything to it. There is more than one coupler type. You see this? So you can just screw it down and you see the cost for number 5.
Oh wow!
It's not really small. But you see this? The good thing about this that all the bolts or the fasteners is going to be kind of hidden, right? Look at this. It's good for columns, but once it comes to beams, look at how big. It's not a small thing. So let's say for number, I remember for number 9, it was like 15-inch long. It was a big piece. So I mean, wow. It is, and look how big, and with a screw. Just
wait. So then,
so
for that particular one, does the rebar? Do they add a screw to it, or how does that work?
No, you screw you add the thread to the rebar yourself.
Oh, okay.
Yeah. I mean, you don't buy the rebar, right? You just buy the coupler from them, and then you can do it this way. So, mechanical couplers are available from time to time. We use them, and look at this. You see this case here? See what happened? You're staggering them because you cannot. You see, you have 2 rebars right next to each other, so you cannot stop the 2 rebars, or you cannot splice them in the same location. So you need to push one up a little bit. Otherwise, and the 2 rebars going to be coming away from each other. You're going to be pushing each other, right?
Right.
Yeah. This is a regular lap splice, which is much easier, cheaper, right? Just imagine that you need to do a thread and you need to put it, and let's say it didn't work well. What would you do, right? It's going to be painful. Yeah.
All right, thank you.
No problem.
Professor, can I get a few clarifications on our submittal?
Sure. Okay.
I have a question for the phi values in determining the development length, phi sub t and phi sub e. Are we?
Which one? So should I go to this slide set?
Yeah, number 15.
Yes, absolutely. Which one?
It's so if you go to the main equation that we learned there, that that one. It's I'm not sure how to pronounce that Greek.
Psi.
Yeah.
Psi.
Psi. Okay.
Psi. There's like.
So for psi sub e, are we taking that our rebars are coated or are they not?
For which one? For ours? No, there's no. Okay, did you hear anything about epoxy coating in your submittal?
No.
No, okay, there's no
Okay.
epoxy coating.
No coding. All right. And then also B sub T.
Psi sub T, yes, for
Yes,
rebar.
sorry, psi sub T.
Yeah.
I'm just by reading the first item, determining the development length for the bottom reinforcement of
Yes.
B number 1. So I take that to be psi sub T will be equal to 1, right?
Yeah, okay.
Okay.
Yes, if psi sub T is going to be equal to 1, this is correct, yes.
And then for lambda,
Yeah.
Lightweight versus normal weight concrete.
Yeah.
Are we?
We have normal weight, so it's
Normal
going to be
weight, okay.
1.0. See, everything is easy in the submitter, right?
Yeah, it's just I don't know. Just
Yeah.
they weren't mentioned in the submittal.
Okay.
So
Yes, yes.
and then also so I know we're finding 3 items. And then you also mentioned to consider number 7 rebars. Are we
Yeah.
considering these number 7 rebars for determining the development length, the hook development, and the
Yeah.
splice length? Okay.
Yes, absolutely.
All right. Okay.
And
Thank you.
no problem. And you have very good examples here. You can follow them, right?
Mhm.
Here, I guess.
Excuse me, that number 7 is for columns only, huh?
I don't have the statement right next to me, but hold on. Project. Yeah. The reason for B1 and B1 top and bottom that I didn't mention because everybody can have different rebar size. So it depends on the rebar size that you use. But for the column, I know that they ask you for the vertical column reinforcing bars to provide number 7. Am I correct?
Yes, yes. That's
Okay, this is
So
only
then for
reason. You see
B1,
that?
we would just use our own rebar.
Yeah,
size?
use whatever that you have there.
Okay, thank you.
Sorry, Professor. So can we take these? Can we apply this number 7 rebars for the
B1?
first 2 items? So the development
Well,
length and the
what
hook
rebar size
development?
did you have in your analysis when you did the design for B1? Did you use number 7 rebars?
I don't know. I have to look.
Okay, so look what have you used and just use it. So if
Okay.
you have number 8, use number 8. It's gonna be 1 inch. If you have
Mhm.
number 7, right?
Professor, the formula says size of T is equal to 1.3 if it's top bar.
Yeah.
I think you mentioned top bar is anything above 12 inches.
Yes,
Yeah, there you go. Thank you.
this is correct. All right, any questions before we adjourn for this evening?
Nope. Thank you.